Where and when do we start our study of the history of science? Well, that can be a difficult question. But most historians of science tend to begin with ancient Egypt and ancient Mesopotamia, and there are good reasons for this. The first reason is that those two cultures exerted influence on the ancient Greeks, and the ancient Greeks, in turn, created the fundamentals of Western thought, the fundamentals of Western history of science, which is the topic of this course. Second of all, both the Egyptians and the Babylonians had the advantage of being literate cultures. Now, literacy makes a great deal of difference. It means there are historical records for us to examine. What we're going to do in this lecture is to run with great speed over the Babylonian and the Egyptian civilizations and to look at the earliest of the ancient Greeks, and then draw some very simple comparisons among the three cultures. Well, the Babylonian civilization was one of several to develop in Mesopotamia. Now, the word Mesopotamia comes from two Greek words which mean between the rivers, namely the Tigris and the Euphrates rivers, the so-called Fertile Crescent, anciently the site of the Garden of Eden, and presently the site of the state of Iraq. Now, as I mentioned a moment ago, Babylonian culture was literate. Well, not only was it literate, it wrote in extremely durable ways. The Babylonians wrote, so to speak, or impressed, which is a better way of stating it, on clay. They used a stylus to make impressions in clay tablets. Now, the stylus that they used left a wedge-shaped impression, and that gives us the name for their kind of writing. Using the Latin word cuneus, which means a wedge, gives us the name cuneiform. The Babylonians were almost obsessive record keepers. We have thousands and thousands of tablets from them. Well, in terms of the history of science, the most important Babylonian activities were mathematics and astronomy. Let's start briefly with their mathematics, starting with their method of writing numbers, because their method of writing numbers is unique in the ancient world. In general, there are two different ways of writing numbers. The simpler method is by aggregation. Now, you're probably all familiar with that in terms of Roman numerals. In aggregation systems, there's a set of symbols which have a fixed value, and we add them up, aggregate them to give us our total number. So I is 1 in Roman numerals, I is 2, I is 3, X is 10, XX 20, XXX, I 32. Okay? The other system is theoretically much more complicated, and that is place notation system. We don't think about it as being more complicated because it's what we use, and so somehow it's familiar to us. But in place notation, not only are there symbols with specific values, but also the position of those symbols relative to one another changes the value. Our system happens to be decimal, that is, in a 3-digit number, for example, the first column on the right is the ones, the next, the first power of 10, 10, and the next one, the second power of 10, or 100. So if I write the numeral 1, that represents 1, but 2 ones does not mean 2, it means 11. Now, place notation, although it's more complicated, is much easier to use for large numbers and mathematical operations. And if you don't actually believe me that it's much easier, let me give you a suggestion. Next year, when it's time to make out your tax return, try doing it in Roman numerals, and you'll see exactly what I mean. Now, most ancient cultures used the aggregation system, but the Babylonians, curiously enough, used both aggregation and place notation simultaneously. Let's say we're a Babylonian and we're starting to write out our numbers for practice. Well, the Babylonian would start out with a wedge-shaped mark pointed down for 1. 2 of them would be 2. 3 of them would be 3, and so forth. And when we got to 9, instead of writing 10 little marks, we'd write a wedge-shaped mark pointing to the left for 10. Aggregation system would work at this point. If we wanted to write 23, 2 wedge-shaped marks pointing to the left and 3 pointed down. But something happens at 59. The Babylonian wants to write 61, for example. He doesn't write 6 marks, and 1 mark. He writes only 2. One pointed down, a space, and another one pointed down, because it's at 60 that the Babylonian place notation starts to function. This is because their base was not 10 like ours, but 60, a sexagesimal system. So a 3-digit number in Babylonian would not have a 1, a tens, and a hundreds place, but rather a 1, a 60, and a 3,600 place. So as you can see, it makes it very easy to write extremely large numbers in the Babylonian system. Now, what were the Babylonians lacking? Nothing. Literally nothing. And by that I mean 0. They had no way to mark an empty place. Now, if you don't think that that's a problem, imagine this. Let's say we're reading along one sunny afternoon on a Babylonian cuneiform text, and we get to a single numeral. Let's say it's the wedge pointing downwards. What is that number supposed to be? Is it 1? Could be. Is it 60? Could be. Is it 3,600? Possibly. Is it 3,600 times 60, whatever that actually happens to be? You don't know. In fact, it could even be 1/60th, because the Babylonians, again, unlike other ancient cultures, used the place notation to go to the right as well as to the left, and so were able to write fractions. Well, at any rate, the Babylonians developed quite a sophisticated mathematics based on this system. There are, in fact, hundreds of mathematical problem texts that survive from ancient Babylon. In fact, they're a little bit disquieting because they're eerily familiar. They always make me a little bit nervous because they remind me of those word problems that we were all forced to do in the 6th, 7th, and 8th grade. Let me just read you one. This is actually from a text from the early part of the 1st millennium BC. The only thing I've done is to convert the Babylonian units of measure and weight into modern ones. A man earns 2 pounds of barley for 1 day of work. In 1 day, he can dig a trench 4 feet deep, 2 feet wide, and 8 feet long. What will the cost be in barley and the time needed for 8 men to dig a canal 6 feet deep, 6 feet wide, and 250 feet long? All right. Well, you might ask, why on earth did the Babylonians choose a base of 60? Okay, well, we can ask, why do we choose base 10? Well, that's an easy one, right? Anybody who has 10 fingers knows why a decimal system works. But why 60, unless the Babylonians were very strangely put together? Well, there are a couple of reasons. One, 60 is full of factors. That means it's easy to take 60 and divide it by 2, 3, 4, 5, 6, and 10, 12, 15, and so forth. And you still get a whole number. Another possible cause may be that factors of 60 appear in astronomical phenomena. There are, more or less, 360 days in a year, so 6 times 60. In that same period, there are 12 lunar cycles, so 60 divided by 5. We don't know for sure which one of these or both it was. I should mention, however, that as strange as the sexagesimal system seems to us, we do actually still use it. How many seconds are there in a minute? 60. How many minutes are there in an hour? 60. How many minutes in a degree? 60. Well, thank the Babylonians for that, because it's their sexagesimal system handed down through the ages that we still use for measuring angles, especially, for example, in astronomical calculations. And it's quite remarkable to think that today's most modern telescopes are still pointed to coordinates in the sky marked out in degrees, minutes, and seconds in a sexagesimal system that was handed down by the Babylonians first and has constantly been used in astronomy for 4,000 years. Well, in fact, it was in astronomical matters that the Babylonians excelled and left us their most important legacy. The Babylonians compiled extensive observations of lunar cycles, of eclipses, of the movements of bodies through the heavens. Why? Well, really, there are two reasons. First of all, it was to regulate their calendar. The Babylonians used a lunar calendar, so their month began with the new moon. They needed to have observations, they needed to know the length of the lunar cycle to regulate that. But their calendar wasn't just lunar because they were an agricultural society as well. They needed to know when the seasons were, when to plant the crops, when to harvest them. So they needed solar observations as well. Well, as a result of generations of astronomical observations, coupled with their very durable records, the Babylonians, certainly by 600 BC, probably earlier, had compiled very complex astronomical tables, which allowed them to predict celestial events. Eclipses, for example. They were able to predict eclipses, the first appearance of the new moon and such things. Now, don't take that too far, because although the Babylonians could predict that an eclipse might happen, they were not able to say the exact time or whether it would be visible. Now, it turns out there's some evidence that priests were sent to various far-flung corners of the Babylonian Empire to watch to see if an eclipse happened, and they would report back on this. But again, they couldn't say exactly where an eclipse would happen, only that there was a possibility of it. What's interesting for us is that they had this predictive ability, apparently without any physical model of the heavens. That is, they don't seem to know what caused the eclipses. They didn't have any sense of how the heavenly bodies moved. It was purely a matter of recording, repeating events that occurred again and again at regular cycles and just extrapolating to the next event. Now, the second reason that the Babylonians were so interested in astrology, in astronomy, was for astrological purposes. The Babylonians, like most other Mesopotamian cultures, had a deep interest in astrology for predicting events. It's not just by accident that the Magi that come to Bethlehem are traveling from the east, because from the east of Judea are the Mesopotamian cultures, and by that point Persian culture, all of whom were very interested in astrology and spent their time looking at the heavens, waiting for portents, and interpreting them. Now, we're going to have plenty of chance to talk about astrology throughout many of the other lectures in this series. The only thing I want to say now is please, please, please don't confuse pre-modern astrology with the horrid fluff that shows up on the funny pages in the newspaper or the cheap little paperbacks in the checkout lines of grocery stores. It's a completely different subject. Pre-modern astrology required a substantial command of mathematical and astronomical knowledge. Moreover, it's very clear that the heavens influence us, isn't it? Well, I'm not going to give you any examples now. But you just think about that. How do the heavenly bodies influence us? We'll talk about that later. In the meantime, let's leave Mesopotamia for Egypt. Now, in some ways, Egypt is a bit more familiar to us. We're used to seeing mummies and pyramids and sphinxes and all the great accomplishments of the Egyptian culture. Egyptian civilization flourished for over 2,000 years, from the 3rd to the 1st millennium BC. However, their mathematics and their astronomy was not actually as developed as the Babylonians. In mathematics, they used a simple aggregation system, none of the place notation of the Babylonians. They also made astronomical observations. You're probably familiar with the fact that various Egyptian temples are oriented along important axes, so that, for example, the sun on a certain day of the year illuminates a gallery, or that a particular portal points towards the rising of a certain star at a certain time of year. What's important here, I think, with the Egyptians is the Egyptian calendar, because the Egyptian calendar is the ultimate origin of our own. Not immediately, it took a couple generations of working on it, which we'll talk about, but in general, the outlines of the ancient Egyptian calendar is the same as ours. A year of 12 months, and they were very rational about it. Every month had 30 days. You don't have to remember any little rhymes to figure out, or count on your knuckles to figure out how many days in an Egyptian month. They're always 30. Now, if you're quick in math, you'll find that that only gives us 360 days. Well, that's not enough. The Egyptians knew this, and they did something very clever. When the days of the calendar were finished, the Egyptians added 5 more days. These were not only uncounted, but they were holidays, festival days for everybody, which, frankly, is not a bad idea. Now, we think about the enormous accomplishments of the ancient Egyptians. We find lots of activities which might suggest development of sophisticated scientific thought. We think about their metalworking, their architecture, glass making, manufacture of various substances. But like the Babylonian ability to predict eclipses, this doesn't seem to have been based on any theoretical principles. It was purely a craft tradition. So that although the Egyptian civilization was marked by long-term stability and incredibly impressive feats of engineering and organization, their study of the natural world was really very limited. Their achievements were tied to practical uses, practical applications, and they didn't stray very far into, as far as we know, into the speculative and the theoretical. In short, they seem not to have asked the central questions of how and why about the natural world. Well, with that, let's move on to the third culture, that of the Greeks. Well, at the time that historians of science first encounter the Greeks, about 600 BC, Greek civilization is not very much to stack up against the towering and ancient civilizations of Babylon and Egypt. Right? Yet, if we turn to a little Greek colony, the colony of Miletus, on the coast of Asia Minor, which is currently a part of Turkey, around the year 590 BC, 580 BC, we're going to encounter one of the so-called 7 sages of ancient Greece, namely Thales of Miletus. Well, if Thales actually wrote anything down, it's long gone. He did not, for example, write on clay tablets. The only knowledge we have of him are 4 ideas attributed to him by Aristotle, 250 years later. And we also have a collection of anecdotes about Thales. Thus, with such little information, it's rather hard to figure out what Thales' actual motivations and actual thought was. But even with the little we have, there are some observations worth making. Perhaps the most important of the ideas attributed to Thales is this one. Everything is made of water. Now, what on earth does that mean, and why on earth did Thales say it? Well, what Thales seems to have been trying to say was that all the myriad of things that we see around us, trees, birds, people, rocks, clouds, it's all at base water. Writing 2.5 centuries later, Aristotle suggested that Thales chose the fundamental substance to be water because every plant and animal relies on water and is filled with water. That's a very Aristotelian thing to say, as we'll see. But there may be other reasons. Thales may have noticed that water comes in 3 different forms. The liquid form we're familiar with, but it can also be hard, as ice and snow. Also, if you leave a basin of water open, it vanishes into thin air, so air itself seems to be water. Moreover, more perhaps historical argument, Thales may have been familiar with Babylonian and Egyptian creation myths, many of which begin with water. In fact, Thales claims that the earth itself rests on water, which is a notion that also appears in Babylonian sources. But the real importance of Thales' statement for the history of science is that it's the first known attempt, at least the Greeks saw it as such, of trying to figure out a single material substratum of which everything is made. It tries to answer the very difficult question, what's the world made of? Well, Thales says it's water. Now, many of Thales' successors would ponder this question. Some would agree with Thales, some would pick other substances. Indeed, if you think about it, the project of answering Thales' question is still going on today in modified form. Nuclear physicists are constantly looking at smaller and smaller and supposedly more and more fundamental particles, trying to figure out what is the stuff the universe is made of. Thales' statement also marks a key recognition of the distinction between the external appearances of a thing and their internal reality. Their internal, unseen reality. That's an important idea. Things are seldom what they seem. We still say that. And Thales is the first case we know of where the viewer is willing to cast aside common sense and common sense perception in order to say something about that unseen, hidden reality. Certainly everything doesn't look like water. That doesn't look like water to me. I mean, I feel a little squishy, but I don't think I'm entirely water. Thales is willing to make the leap to say everything is water. Now, this distinction between appearance and reality is going to be key for the early Greek thinkers. And later Greek thinkers credited Thales with launching this project. In a sense, then, this one sort of mysterious line of Thales is worth more to the history of science than 10,000 Babylonian eclipse records. But let's not quite write off those Babylonian eclipse records yet, because Thales became a celebrated character of Greek antiquity. His reputation reached mythic proportions, so there are lots of stories about him. One of them that his fame rests upon is, according to Herodotus, he predicted a solar eclipse which occurred during a decisive battle between the Lydians and the Medes. Now, you may have seen in Hollywood films these great scenes of an eclipse happening in the middle of a battle. I think there were several films that incorporated that. That's actually a reference to Thales. According to Herodotus, he predicted the year in which this eclipse happened. We can do our astronomical calculations backwards and find that an eclipse did happen that was visible in Ionia, where the Medes and the Lydians were fighting in 585 BC. Now, if it's true that Thales did predict this, and we don't have any good reason to doubt it, he probably used those Babylonian tables to make the prediction. It was, however, a good piece of luck, one, that it was visible in Ionia, and it happened quite by chance that it was during a decisive battle between the Lydians and the Medes. But Herodotus, the historian that recounts Thales' feat, only says that Thales set the limits of the year in which this eclipse would happen. Thales is also supposed to have diverted the course of a river in order to allow an army to cross it. Well, I have my own favorite stories about Thales of Miletus, and they're considerably less monumental than this. One recounts that Thales, who made observations of the heavenly bodies, was out walking in a field one night, looking up at the stars, looking up at the planets, and as he was walking across the field, he stumbled and fell into a ditch. And a slave girl had to come along and help him out of the ditch. And she laughed at him and she said, "Thales, Thales, you know everything about the heavenly bodies, but you don't even know it's beneath your own feet." Right? Well, you can see that the image of the absent-minded professor has been with us since ancient Greece. Even though it doesn't tell us anything presumably true about the life of Thales, it tells us something about the ancient Greeks that told and made up this tale. But, according to Aristotle, Thales had his revenge, because Aristotle tells us that at some point the citizens of Miletus were mocking Thales on the grounds that he was supposed to be so smart and he was still a poor man. So Thales used his knowledge of the heavenly bodies to predict a huge olive crop the following year. When the winter came, Thales went around to the olive presses and bought them all up. The next year, the bumper crop came as predicted. All the citizens of Miletus needed the presses, and Thales found that he could rent them out at whatever terms he liked. Well, it's very unlikely that the story is true. It would be more a matter of luck than skill to predict a large olive crop based upon the positions of the heavenly bodies. But it does point out the division between practical and theoretical knowledge of which the Greeks were keenly aware. Moreover, the story of Thales and the olive crop clearly puts theoretical knowledge at a higher level than practical applications. In other words, this is to say that the wise, the natural philosophers, could always use their knowledge to become rich if they cared to, but they simply don't bother with such comparatively trivial pursuits. Now, this division between theoretical knowledge and practical application is going to come up again and again throughout our study, not only in the ancient Greek culture, but also in the medieval world as well. Well, now I think we've come to the point where we need to compare Thales and his Greek followers with the Egyptian and Babylonian predecessors. Now, it's unquestionable that Thales knew of Egyptian and Babylonian astronomical and mathematical work. Some accounts of him say that he traveled to both empires, and there's no reason we should disbelieve this. Miletus was a trading center, and Thales could have easily hopped on a boat and sailed to Egypt, where there was trade with the Milesians. He easily could have followed one of the trade routes to Babylon. But Thales' work, or at least that of his followers that we know more about, is distinctive from the Egyptian and Babylonian work in several important ways. Now, one of these ways is, first of all, we know Thales' name. Is that significant? Well, yes, probably it is, because we have no similar names to attach to Babylonian and Egyptian ideas. Thales was an individual with individual new ideas, and new ideas, so it seems, that were often in conflict with those of his neighbors. He even founded a distinct school of thought that carried on his ideas, his methods, his questions, called the Milesian school. And we're going to discuss the Milesians in the next lecture. Second, although Thales did engage in practical activities, and I don't just mean olive presses. For example, he supposedly gave recommendations for sailors how to navigate at sea. He also purportedly developed a method for determining the distance of ships at sea, by triangulation, one would think. But he also engaged in what we would call philosophical speculation about nature, to uncover the knowledge of things that did not actually have immediate practical application. It's hard to imagine an immediate practical application of all things are made of water. Thirdly, and I think probably most importantly, Thales stands at the beginning of a tradition in Greek thought which involved the systematization and explication of observations and the search for hidden causes and principles in nature. The claim that everything is made of water may seem extreme or odd or maybe just plain wrong to us, but the fact that Thales, and more importantly his followers among the Greeks, the fact that they were thinking this way marks a crucial development in human history, seeking for the reality beneath the surface of natural things and groping for the hidden causes behind even everyday observations of the natural world. These are central features of the Western philosophical and scientific tradition. And here we see them being born in Miletus at the beginning of the 6th century BC. Now, at present, we find very little evidence of this kind of thinking among the Egyptians or the Babylonians. I would say, to be safe, that there's a huge amount of Babylonian cuneiform writing out there. Maybe in one of those texts there's something like what Thales was doing. At present, we're not aware of it. So, despite the engineering ability, the military might, the administrative prowess of Egypt and Babylon, these were far in excess of early 6th century Greece. But nonetheless, the intellectual legacy that started in Greece has more to do with the history of science, is a greater contributor to it than the legacy of Egypt or Babylon. And it boils down to this, I think. Much of that Greek legacy depends upon a very simple notion, call it a belief or even a credo, and this credo remains at the core of modern scientific inquiry, namely that the world is a regular place. It is not incomprehensible, it is intelligible. Phenomena are caused by regular causes operating in the natural world which are intelligible even though they may be hidden. Now, in the following lecture, we're going to look at Thales' successors and how they developed on the lead that Thales left to them.